I welcome you all. Yeah, I think I should start again then. Yeah. Good evening, everyone. On behalf of ISI Bangalore student, I welcome you all to the Limit Mathematics Online Camp. It's a great pleasure for me today to introduce our speaker, Professor Anubhav Mukherjee. Professor Mukherjee was once an ISI student. He did his BMath and MMath from ISI Bangalore, and then he obtained his PhD from Georgia Institute of Technology. He was then a postdoctoral fellow at MSRI and also served as a instructor at Princeton University. Currently, he is an assistant professor at Princeton University, and his research areas include low-dimensional topology, contact, and symplectic geometry. Today, he is going to give us a presentation on wild world of four manifolds, and it's a great honor for us to welcome him to present a talk in our Limit Mathematics online camp. So over to you, Professor.
Okay, yeah, thank you very much. And is my screen visible to everyone?
Yeah, if your screen is visible.
Okay, great. Yeah, so I don't know. I was thinking what to talk yesterday, and I thought that I'll give some interesting elementary talk on mostly topology, but a little bit on four manifold as well. So um and also I encourage everyone to switch on their video so that I can see people instead of like feeling like I'm talking to a wall. Uh you know so and also it would be more interactive. I don't know, I haven't prepared much. I want to say something very elementary, so maybe all of you probably know everything that I'm going to say, so if I bored any of you, sorry in advance. um okay, um okay, what do I want to say? So in topology, so in topology, one of the primary object to study is classify manifolds. Okay, so I'm not sure anybody's background, so but I feel that since I was told that they are all first or second year of undergrad, probably you don't know the meaning of manifold. So let me now first introduce what is manifold. So what is manifold? In order to understand manifold, first we need to understand the idea of dimension. So so the idea of dimension. So let's, for example, imagine that you have a string, and then there is an ant sort of walking on the string. In this situation, this ant kind of have only 1 degree of freedom, in a sense that it can go either forward, or the reverse operation of this is sort of going backward. So there is only 1 degree of freedom. But now, if I replace this ant from the string to a page of paper, then it has now sort of intuitively 2 degree of freedom. The forward movement is still there, forward and backward movement, but now there is sort of up and right. And notice that these two movements are sort of linearly independent. So these two movements are deep. And this is all you need to travel from any point to any point in this page of in this sheet. So from any point, one can travel by these two movements. So this is sort of the idea of then dimension 2. So in other, then dimension 3 would be if you imagine that this ant now can start flying. So if you know now that this ant can also fly, then it will unlock the third dimension. And now let's imagine that with flying ability, it also get an ability of time traveling. In that case, it will unlock the mystery of fourth dimension. And so on, we can now abstractly define dimensions, the idea of dimension. You can sort of keep adding new independent direction that was not uh, um, be achievable by any other previous operations. Okay, so then with this idea of dimension, we can define an n-dimensional manifold. Yeah, by the way, feel free to interrupt me, because as I said that I am not sure whose background is what or how much people know about topology and everything. So if anything I says that confusing or you don't understand, just stop me and let me know. Okay. Okay. So we call this object manifold if locally it looks like an n-dimensional Euclidean space. That is, around every small point, it just looks like a Euclidean space. Globally, it could be very different. And now we'll talk about that part. Okay. So it's very vague. As I said, that in this talk, I'll not properly define anything. And my idea is to sort of give a very hand-wavy idea of how things work. Okay. So now, as I said, so now we define this object manifold. And now this is where everything started getting more interesting, because, for example, take an example. If you look at the surrounding where you are at right now, you observe that it is a flat plane. Like if you just look at your leg and you see that you sort of standing in a flat surface. But on the other hand, we know that we are all standing on the earth, and the surface of the earth is sphere. So on the Okay, so this is where the interesting question starts. Then how do we know that we are in a sphere? How do we know that we are not just in a plane, but we are in a sphere, right? So how do we mathematically conclude this? Okay. So this type of problems in general in the world of mathematics called classification problem. That now we have to sort of classify, understand everything. So these are sometimes also called classification problems. Okay. Um, okay. So we can draw some conclusion from history, right? Like in history, we read that in ancient times, sellers started selling from a point, and eventually they come back. So, so in other word, sort of sphere has that property, right? If you are in a sphere, if you start sort of moving from a point, you follow the great circle, you sort of eventually come back to that point, right? So this is sort of observation from history we can take. So we can say that, oh wow, sphere has this property, so it must be a sphere. But is it? There could be another surface which has the actually same property. For example, take sort of the donut shape or the tube shape. In this also situation, if you start from one point and sort of started going, you eventually come back to the point. Or if you go this direction, you also come back. Okay. So then the question is that, are these two shapes same? Of course they are not, right? Because we can see that one is different from the other. But how do you prove that mathematically that these are different shapes? Because now we have to build some mathematics to conclude that they are not same. How do you do that? So anybody would like to guess anything? I mean, if you know the answer, don't say the answer. But if you don't know the answer, you're seeing this for the first time, do you have a guess? So, so what's the intuitively what we can see? We can see that there is a hole, right? But now the question is that how do mathematically define the meaning of hole? That really a very sort of intuitive idea that there is a hole and maybe like we cannot pass through the hole, something like that. But what is the meaning of mathematically understand that there is a hole, right? Um, so how do we sort of mathematically define the idea of hole? Um, so one thing note that okay, so let's sort of again try to understand these two these two objects and see what sort of different situation we can find. So one thing we should notice that in this situation, um, if I take any loop here, oh, sorry, um, and let's say this is my north pole, okay, then I can sort of push everything to the north pole, right? Sort of in a nice way. And if I do so, then this loop can be shrink to a point, right? So this loop can be shrink to a point. And the interesting part is that it can be shrink without breaking the loop. So without breaking the loop, okay? On the other hand, now let's notice this object, right? The torus. In these objects, for example, if I take this particular loop and if I allow the rule that I cannot break this rule, break this loop, then there is no way I could shrink this loop to a point, right? So this loop cannot be shrunk to a point without breaking. Okay, and so that's sort of a mathematical distinction distinction between these two objects now. That one object I have where all loops can be shrunk to a point, and then the other object I have where there are loops that cannot be. And so then I could conclude that, okay, mathematically these two objects are different, right? Because if these two objects are same, then they should have same properties. So, so the idea that we used here is sort of, we used loops, or sometimes in more concrete mathematical terms, this is called knots, to um, distinguish two manifolds. In general, now we'll see more that sort of this idea played in general a big role in the theory of manifold, that we see how smaller subset sitting inside manifolds and how they interact, and that sort of characterize or determine the property of the bigger manifold. So the underlying idea that we'll be more talking about is sort of this. We use this sophisticated term submanifold, but we just mean that sort of smaller dimensional manifold sitting inside a manifold. Like if it's a 3-dimensional manifold, you can think of 1 and 2-dimensional manifold could be sitting inside. So submanifolds inside manifolds helps us to characterize. Okay. All right. So far, anybody has any question? So okay, so now we'll talk some modern question on this basis. So this is sort of the 2-dimension question, right? So in 2-dimension, we see that a sphere, one way to understand a sphere is that if the loops are kind of shrink to a point, right? Then we can say that this is a sphere. Okay. And then there is sort of classification result saying that essentially you can understand surfaces essentially through this process. Okay. So the question started getting interesting now in 1905. The French mathematician Poincaré asked or proposed this following question. So this is the famous question known as Poincaré conjecture, which says that if you have a closed 3-manifold where any loop can be shrink to a point, there is a small thing we need is that this base point homotopy, like fixing a base point. But you can ignore that part. Then it is a 3-sphere. Okay. Or it is, let's say it is, so I have to define one term. It is same. Oh, sorry. Yes. Okay. This is pretty bold statement. I mean, so the beauty of math is that if it is so simple that you believe this is like it is so simple that you can understand once you see these questions, but it is so difficult that you don't know how to solve this problem. That sort of is the essence or beauty of math. And this is that famous question that he proposed in 1905. Um, um, okay, so let me sort of define things more precisely now. That what is the meaning of same? Like you can see that there are various terms, right? I use like same as what is the meaning of being same, or like what is the meaning of loop and all. So okay. Um, but again, anybody has any question regarding the statement of what I wrote here? Okay, so sorry,
Is it only for three manifolds or is it for n-dimensional manifolds?
I'll come back to that question. But the original question was only for three manifold.
Okay.
Okay, so um, okay, so sphere. So how do you define a sphere? Let's think for a moment. So this is probably you all know what is the equation of sphere, right? That you take a polynomial with n variable. So p is x1 square plus x2 square plus xn plus 1 square. Then an n dimension sphere is nothing but the solution of all the points where p equal to 1. Right? This is the idea of, this is the definition of sphere in general we use, okay? Okay, so now we have to understand the meaning of same, that what is the mathematical meaning of like two things are same, right? So what is the idea we are using here? Um, so the notion of same, so there are sort of two things we will define here. Okay, so let's think of this way. So let's say one more thing I have to define here is that, okay, closed. So I don't know whether you all are familiar with being closed or not, but closed mean a compact and no boundary. So like a disk will not be considered as a closed manifold because it has a boundary. So anything which is compact but no boundary will be called closed. Okay. All right. Okay. So now let's define the idea of same. Okay. So let's say Xn is an n manifold. So we'll say that this is same as a sphere if sorry, if there is a map from X to Sn, let's call it F, such that F is continuous. We can also interestingly define another category, which is sort of imagine that not only this is a continuous map, but also you can differentiate the map. So sometimes it is called smooth. Okay. Where, so in other words, you can think of that this is a continuous map, but not a smooth map, a graph of like this, but this is a smooth map where every point you can differentiate. Okay. So there are two categories we can essentially define. One is continuous, one is smooth. Okay. Smooth is sort of stronger than being continuous. Okay. So F is continuous or smooth. Um, this is F is bijective and F inverse is also continuous or smooth. Okay. So this is the meaning of being same. Okay. That is, then we call their same. So in the case of continuous category, we call this as homeomorphism. In the case of smooth category, We call it diffeomorphism. Okay. So is this two terminology clear to everyone? Okay. So okay. So one more thing now I have to define is that okay. So um okay. So now let me tell you this. So in my mind, this is sort of the biggest question in the modern topology that shaped the modern topology. So, so to my opinion, this question sort of shaped the whole modern topology. Like last 100 years of topology kind of dominated by this question, or people try to understand this question, or in order to understand this question, people develop many beautiful theories, which may or may not related to exactly this question, but this is the question which is sort of shaped the modern topology in last 100 years. Okay, so one could now generalize this question. So how do we generalize now? Um, so one, so as I said, that this is sort of the simplest form, but essentially, given a manifold Xn, one could associate something called some kind of algebraic object to this, which is called homotopy group. And roughly speaking, these homotopy groups for n manifold, there would be homotopy groups pi1, pi2, up to pi n. So pi1 is sort of, as we saw, that sort of track the loops. These sort of intuitively track loops. Pi2 is sort of intuitively track surfaces in the manifold. So like kind of track. Similarly, pi3 track like some kind of three-dimensional objects and so on. Okay, so this is sort of the intuitive idea that we sort of track all these kind of classes of objects. So one interesting feature of a sphere is that if you have a sphere, then all these homotopy groups are actually trivial. There is no interesting homotopy group exist for a sphere. So with that notion in mind, now we could sort of define the generalized Poincare conjecture as, so then,
You mean for k less than equals to n minus 1, right? Go ahead.
yeah, yeah, anything bigger than that is sort of intuitively zero. So yeah, because there is no space, so vacuously true. Oh yeah, sorry, pi n,
Yeah,
pi n, yeah.
yeah, yeah.
So generalized Poincare. Um, okay, so what does generalized Poincare conjecture says that it's saying that if you have a closed n manifold with all these homotopy groups as zero, then it is a sphere. Okay. Again, sounds like a very stupid question now. Like this is impossible. In a sense that, like maybe like 100 million some dimension, this is not true. I mean, this is kind of amazing if such a statement turns out to be true, because it's sort of impossible. Like how could this is such a simple description of sphere? There could be some weird object that also could have the same property. And this is where sort of this whole development started. These sort of ridiculous questions that seems like almost impossible to say anything about started having answers. So the first breakthrough kind of came by Stephen Smell. And he proved that actually, if the dimension is bigger than equal to 5, and if xn is as above, then X is homeomorphic to a sphere. So by homeomorphic, I mean in the continuous category. So this is, in my mind, one of the biggest breakthrough at that time. And he, of course, win Fields Medal for this theorem. So he won the Fields Medal for this. Okay. And he developed some groundbreaking theory in order to prove this. So this is the first breakthrough came, or actually no, I'm sort of twisting the history a little bit. But anyway, so so this is what he proved, that it is homeomorphic. Okay, but then you could also ask that, okay, what happened to the diffeomorphism category, right? Is it diffeomorphic? And this is where the next theorem comes. So then John Milner came, and he shows that the 7-dimension sphere can have 28 different smooth structure. In other words, if you just think of 7-dimensional manifold as a manifold, then you can give some smooth structure G1, G2, G28, such that none of these Gi and Gj's, these smooth structures, are sort of diffeomorphic. They are homeomorphic, but the moment you want to construct a smooth map, that will get destroyed. So this continuous map cannot be made smooth. And which is so surprising, because in math world, we never saw such phenomena before. We used to think that homeomorphism is same as diffeomorphism, because like just imagine intuitively, right, that if you, let's say, a graph of a manifold looks like this, right, then we can sort of spark up this by like a little bit and make it smooth, right? So we always used to think that whatever is continuous, you can make it smooth. You can sort of see all these bad points and sort of change a little bit around that and make it smooth. So this is sort of the first surprising phenomenon when happen, is that like the continuous map cannot actually make smooth in an obvious way, which is sort of super surprising. And in math world, such phenomena is called exotic phenomena. So that is, they are homeomorphic but not diffeomorphic. That is. Okay. All right, great. So so this is John Milner. Okay. And then in 1984, Friedman came, Mike Friedman. And Mike Friedman showed that even in dimension 4, roughly it is true in a sense that in dimension 4, if you have a manifold with this property, then X is homeomorphic, again, homeomorphic to 4 sphere. Okay. And finally, by the way, he also wins Fields Medal for this theorem. And then finally, Perelman came in 2003. So this is 1980. This is 2003. And who proved that in 3 dimension, it is diffeomorphic to sphere. And again, he was awarded Fields Medal for this, but he rejected because of various controversies. Uh, so yeah, so as I said, that this is one of the most influential problem in topology, and which sort of shaped the modern world. Okay, so now we sort of focus on this particular exotic phenomena, because the theory that Smell and Milner developed, they can sort of understand all this nature of homeomorphism or diffeomorphism in higher dimension. That is, as long as this dimension is bigger than equal to 5. And Perelman's theory is saying that in dimension 3, there is no difference. Homeomorphic is same as diffeomorphic. But then there is this one sort of single standout result where it is saying that it is homeomorphic, but now we do not know whether it is diffeomorphic or not. So one of the very interesting open problem right now is that whether, so the question or conjecture is that S4 has unique smooth structure. Okay, so now let's try to think a little bit about why this question is interesting or difficult or whatever. Okay, so one of the way to approach this problem is sort of use Smell's idea. So what the Smell idea. Okay, so what Smell did, so Smell developed this theory called H-cobordism theory. So he developed something called H-cobordism theory. But the idea of this theory is sort of he could understand when two things are same, if he could understand the submanifold. As I said, that the strategy is always to sort of use some kind of submanifold inside a manifold to understand things. And in his theory, he sort of developed this idea of when like sort of two submanifold can make disjoint. Okay, that was sort of his key idea, to like when he can make things disjoint from each other, then he can sort of like define some nice maps from one to another. Okay, so in this theory, one of the key idea was to be more precise, the key idea was to look at surfaces in N manifold. Okay, looking at interesting surfaces which we can think of two-dimensional objects in N manifolds and try to make them disjoint. Okay, so now you can ask that why it only worked for dimension bigger than equal to 5. What is so special about the number 5? So let's think for a moment again. Okay, that how come this magical number 5 shows up? Just for an example, let's think of an example, right? Let's start with this first example that we did, right? A torus. In the torus, let's say we take two one-dimensional surface, like sorry, two one-dimensional manifold, right? So one is this loop, and one is this loop, right? Now notice that no matter what we do, we really cannot make them disjoint, right? Without breaking the loops, no matter what we do, they are always intersecting. We cannot make them disjoint. Cannot make them disjoint. But now notice that if I put this torus in a 3-dimensional space, okay, so let's say now if I put this same torus inside a 3-dimensional space, okay, then notice that now I have an extra dimension, right? And I can use this extra dimension freedom to sort of push one of the loop maybe up right? And if I do push one of the loop up, then they are disjoint now, right? In a sense that just think of this local picture, right? So I have this picture, but now I have an extra dimension. So like they are intersecting this, but if I push one up a little bit, then now they are disjoint, right? So I could just like push one of this loop up, and then they sort of looks like this, right? So they become disjoint, right? One is sort of up of other. So this is what happened, right? Extra dimension help us to make things disjoint, right? So the key idea was here is that 1 plus 1 equal to 2, which was the total dimension. That's the reason we cannot make things disjoint. But in this situation, 1 plus 1 is less than the total dimension, which is 3. And for that reason, now we have an extra dimension that we sort of push and make things disjoint, right? Okay, so and as I said that, we sort of in Smell's theory, he was looking at two-dimensional objects, right? So what is 2 plus 2? So we all probably know this answer, that 2 plus 2 is 4. So as long as your total dimension is bigger than 4, then you can apply this idea, this same idea that I'm sort of trying to explain here, that you kind of make things disjoint. And with that, then sort of Smell's theory work. Which is sort of very magical in my mind. That so the problem in what appeared is here is that the 2 plus 2 equal to 4. That's the reason surprisingly 4 dimension become extremely difficult to study, because all the theory that sort of worked in high dimensions somehow absolutely failed in 4 dimensions. And Perelman sort of used a completely different idea, which is sort of very limited, in my opinion, so far in dimension 3. There are some recent developments by Gromov and all, but again, I still don't think this is super promising. But again, maybe some of you can one day solve it, or maybe not. Who knows? Um, so then, as I said, that so the interesting question right now is to understand what are or how many smooth structure a force sphere could have. Okay. So let's take a step back from force sphere, and let's imagine now that you take a point out from the sphere, right? Then we know that what is this manifold, right? This manifold would be nothing but an Euclidean space, right? Because we all probably see this sort of trick that if you have a sphere, you put a light bulb here on the North Pole, and then you sort of look at the reflection, right? You sort of look at how every point, like look at the stereographic projection from this point, and this will give you a homeomorphism or a diffeomorphism from a point to like sphere minus a point to the Euclidean space, right? Okay, so one could also ask the question that, okay, fine, like we want to understand sphere, but do we know anything about Euclidean space? And sort of here is the very interesting theorem, is that, so let's say Rn is n-dimensional Euclidean space, okay? So Rn has unique smooth structure if and only if n not equal to 4. And R4 has uncountably many smooth structures. So which is so surprising that the four dimension is somehow the weirdest dimension, in a sense that if you go outside four dimension, then there is nothing wrong happening. It's like everything follow the rule. The moment you stepped into the dimension 4, everything started go south and nothing follows the rule anymore. And this is the idea that that R4 has sort of uncountably many, in fact, smooth structures, and any other Euclidean space always has unique smooth structure, in a sense that if it is homeomorphic to any other space, then it is also diffeomorphic to that space. There is no problem. But in the dimension 4, this is a huge problem, that it can have some kind of wild structures. However, this is not sufficient to answer the question for four sphere, because you really cannot push those smooth structure to a four sphere, sadly. And over the years, mathematicians found, except four sphere, there are other manifold in dimension 4 you can think, and in various such manifolds, people found existence of this sort of interesting exotic structure. So we know many examples of four manifolds with exotic structure. But again, four sphere is still out of reach for us. We haven't had any idea how to understand the smooth structure on four sphere. So I'll sort of end this talk with this question, that whether four sphere has a unique smooth structure or not. And yeah, I think this is a good time I should stop. And yeah, I'm happy to chat if anyone interested in, but
Yeah.
So when you say smooth structure, what exactly do you mean? Can you give an example of something in lower dimension, for example, R3 or something?
oh, as I said, it's sort of a metric, uh, which is sort of gives you like smooth structure, in a sense. As I said, the one way you can think of is so um, yeah, I do not want to go to this whole formal definition, but it's sort of like you um, okay, how do I say it? So the way we can build manifold is we sort of define sort of atlas, like local Euclidean space, and we sort of glue them patch by patch nicely together, right? So if those gluing maps are smooth, then we call this overall structure smooth. But it's not necessary that the gluing map has to be smooth, right? And so smooth structure is sort of, you can think of that when gluing maps are smooth. But then the question is that, can we use different gluing maps? And does that gives you different structure or not? So this is roughly you can think. Sorry, do you mean, sorry, what? Could you ask the question? Sorry, I can't see the chat.
Yes, somebody in the chat has asked whether you mean a different, like the smooth structure means some kind of derivative.
No. Smooth structure doesn't mean
Yeah.
derivatives. Structure helps, like, so smooth structure helps you to define calculus, in a sense that help you, like, so in other sense, as I
I
say,
mean,
just
different definition of derivative. different kind of derivative actually.
Sorry, so I can't hear.
I mean, by this smooth structure, you can define a different sort of derivative, different definition of derivative. Like for the plane, uh, we define the derivative limit h tends to 0 f of a plus h minus f a by h. So for different smooth structure, a smooth structure means different definition of derivative. We can define.
I don't know what you are meaning by this. Sorry.
I had a different question actually. So when you were talking about Small's theory, so like basically what we are doing, we are trying to like do a transversal intersection between manifolds over there. But like,
Mhm.
how is it helping in like classifying? What to say? Like the classifying theorem that you were saying. Could you just give a brief idea about it?
Yeah, so it's sort of very non-trivial, but as I say, I lied in many places. Um, the idea is to sort of build a cobordism from one manifold to another manifold, and then showing that this cobordism has sort of no. So, like you can think of there is a map from this cobordism to R. Sometimes you think this is a Morse function. I don't know. These are, if you don't know this term, that's fine. Since somebody asked me, I'm trying to say. Um, and then the idea of smell is sort of modify this Morse function so that it has no critical point. The problem occurs is that it could have index 2 and index 3 critical point, index 3 and index 2 critical point. And these critical points sort of intersect around like surfaces. Um, and so the goal is to having a Morse function with no critical point. So that means that you have to sort of delete this Morse function. So in other words, you have to make the surfaces corresponding to them to be disjoint so that you can cancel them out. And that's where the idea comes.
Okay, thanks.
Yeah.
So also like what are exactly the manifolds X and Y we are choosing over there?
Um, so essentially X is the regular sphere and Y is probably something which are same homotopy group as
Oh,
this.
like so if there are any questions, you can ask them in the chat or you can maybe turn on your microphone and ask them.
How are homotopy groups pi1 to pi are defined? Means what are they actually doing?
Sorry, repeat the question. I can't hear.
My question is, how are homotopy groups pi1 to pi are defined?
Oh, so essentially you look at map from K sphere to your manifold and with a base, fixing a base point. So you fix a base point, let's say North Pole here, and a fixed point P. So N goes to P. So you look at all such maps and up to homotopy. All maps up to base point homotopy. So you cannot move the base point. Base point. So this is sort of the definition of pi k. Now you can prove that maybe as an exercise that pi k of Sn is 0 when k is less than equal to n. Maybe you can try to prove that. Oh, sorry.
Like one way I know to prove this is using like you can homotop any map to a cellular map now since SN won't have any K cell. Like you can give SN a CW structure without a K cell, then those have to be like nullified. Those maps have to be nullified.
Yeah, that is a good enough proof, I guess. Or as I said, that for cheating, you can assume that this is a smooth map, and then you can sort of homotopy to a map which missing a point, and then you sort of use the stereographic projection kind of to
Ah,
define. Yeah. Yeah, there are many ways you can prove that. Yeah.
hmm. Okay, if there are no more questions, let's thank our speaker. Uh, Thank you, Professor Mukherjee, for giving such a good talk. We hope you had you will we will meet you again sometime when we conduct our online competition next time. So
Okay. Yeah,
thank
yeah.
th thank you everyone for being a part of this talk. We will meet again next day. The details will be given in the community chat.
Okay. Wait, I need
Thank
to
you.
disconnect my thing, right? How do I? Okay, great.